So in this example, I want you to write this as a single trigonometric function. 1 minus sine squared of t divided by cotangent squared t. So within this division, we have multiple trig functions, right? We want to somehow write it as a single trig function. So if it involves addition, then you might want to find common denominators and add the terms together, like you had to do back in intermediate algebra. Here, we've got a single fraction, so we're good to go here as far as that goes. If you had two separate fractions, you might want to get a common denominator and add together. So that's not an issue. So take a look at that numerator. 1 minus sine squared of t. Now, if you know the answer, don't shout it out. Let's go back and look at our identities that we're supposed to have memorized. It doesn't quite look like any one of them. But the idea is you not only use these identities, you can manipulate them algebraically to get other identities. So you can assume these are true, and you can also assume the identities that you get by just regular algebraic manipulation. You can assume those are true as well. So take a look at that Pythagorean identity. What would I get if I subtracted, say, sine squared from both sides? So if you think of this as an equation and you subtracted sine squared t from both sides, there's actually a couple of different ways you could do this. You could also subtract cosine squared. I'll do that in a second. If you did that, what would you end up with? You'd have cosine squared t left. What would you end up with on the right side? Oh, that looks familiar, doesn't it? So you need to get to the point where you recognize, oh yeah, 1 minus sine squared t, that's the same as cosine squared t from the original Pythagorean identity. What's the other way it could be? You could solve for sine squared t. What would you get on the other side? 1 minus cosine squared t. So yeah, and that's just, it's like you're solving the equation for, in the case in purple there, the cosine squared, right? Now you don't prove identities that way, but you can manipulate known identities that are already proven that way. Okay? So long story short then, I can replace 1 minus sine squared t with, in this guy, cosine squared t. So this guy that's given is the same as having cosine squared t on top, cotangent squared t on the bottom. We're still not there yet, but it's closer to being a single object than it was before. We're trying to write this as a single function, right? So we're not quite there yet. What about cotangent squared t? Could you rewrite that using one of those ratio identities? So what do you know about cotangent in terms of sines and cosines maybe? It's cosine over sine. So then here's the big idea for that. Okay, if cotangent is cosine over sine, then what's cotangent squared? Cosine squared over sine squared, because the exponent of 2 splits up over division. So I'm going to leave the top the same, cosine squared t. That denominator, I'm going to replace it with, that's cotangent squared, so I'm going to replace it with cosine squared t over sine squared t. So that's the denominator. That part in purple is the denominator of the big fraction. So I'll make this division bar bigger to make that clear. So we're dividing the guy in blue, cosine squared t, by that fraction. Everybody agree with that? Okay. Now, when you divide by a fraction, that's the same as what? You can multiply by the reciprocal of the guy in purple. I'm going to switch everything to blue now. And I get cosine squared t times sine squared t divided by cosine squared t. Everybody with me? Okay. As long as the operation is multiplication, if this were a plus sign, this wouldn't work. As long as the operation up here is multiplication, and down here, as long as it's either a single function or factors, multiplication is the operation, it's okay to do what? Divide it out. Cosine squared divided by cosine squared makes 1. So this is the best we can do. We have a single function squared. Sine squared t is our answer. Now, you do have to remember that there may be more than one answer to these types of problems, but this is probably the best one here.